The game of pool is loved by millions of people everywhere. From casual basement games to professional championships watched by millions. The game of pool can even be found on our phones and computers. From simple shots that require slight angles to more complex ones. The physics behind pool is truly amazing. In this video, you will see how physics apply to the game of pool. But first, let's go back. Pool was first played in the 15th century as a lawn game, similar to croquet. The game was eventually moved to a table, and green felt was used to replace grass. The maces originally used became unwieldy for the tabletop version. Players began to use the handle instead of the large mallet end. Soon, cue sticks were developed to replace the mace entirely. As the game gained popularity, more adjustments developed. Pockets were added and side rails replaced the clunky walls. Pool halls developed for public games. People began to place bets, or pools, on the game, and the name stuck. Pool became the popular name for the game of tabletop pocket billiards. François Mingaud, a French captain under Napoleon, played a vital role in the development of the game while imprisoned in Paris in the early 1800s. By using scraps of leather on the end of his cue, Mingaud discovered spin could be produced due to increased friction. Mingaud was said to have asked for a longer sentence in order to continue his study of the game on the prison pool table. Many variations of the game developed, and today 8-ball, 9-ball, and straight pool are among the most popular games. Players try to pocket certain balls by hitting them via the white cue ball. In 8-ball pool, a commonly played game, a player wins by successfully hitting the black 8-ball in after hitting all of either the solid or striped balls. The physics behind pool is what makes the game so interesting. In this video, you will learn how force relates to mass and velocity. You will also learn how mass and velocity relate to each other in collisions. You will see how torque can be produced by hitting the cue ball at different heights and at different forces. And you will learn how angles of approach and angles of departure can play into hitting shots that are at tricky angles. Let's look at the first formula. Ft equals mv. In this formula, F is equal to force, T is equal to time, M is equal to the mass, which will be the mass of the cue ball, and V is equal to velocity, or speed. Let's try a word problem with this formula. During a break shot, a player hits the 170-gram cue ball so that it travels at 5 meters per second. If the cue ball is in contact with the cue stick for 3/100ths of a second, what force is applied on the cue ball? Okay, so for this problem, we know the time that the cue ball is in contact with the cue stick, which is equal to 3/10ths of a second. We also know the mass of the cue ball, which was 170 grams, or that's also equal to 0.17 kilograms, which is what we need to use for this formula. We know the velocity, which was 5 meters per second. What we don't know is the force. So to change this equation for force, we can simply divide by time, which will give us force equals mv over t. Now all we have to do is plug in these numbers to find force. So force is going to be equal to 0.17 kilograms times 5 meters per second over 0.03 seconds. With a quick calculation, we can find that this number is going to equal to about 28.3. So this is the amount of force that would be applied on the cue ball after being struck. Now, what would change if instead of 5 meters per second, the ball only traveled at 3 meters per second? Well, all we'd have to do now is change this 5 to a 3. So we would get force is equal to 0.17 times 3 meters per second over 0.03 seconds. All that's going to change for this is that the force is going to be slightly decreased. The approximate force that we are going to get here is about 17 newtons. Now, what if instead of 3, the ball travels at 7 meters per second? Well then, we do the same thing, we switch out 3 with a 7. So we're going to have force equals 0.17 times 7 meters per second over 300ths of a second. In this calculation, the force is going to be about equal to 39 2/3 newtons. Now, newtons, what does this mean? 39 2/3 newtons is about 9 pounds per second, which is almost as much as 2 bricks, because if you estimate 1 brick equals 5 pounds, you can see that hitting the cue ball at this speed is almost equal to the force of 2 bricks hitting it. In this break shot, a high force is used, which makes the cue ball achieve a higher velocity. Let's look at this next equation. M1 V1 equals M1 V1 final plus M2 V2 final. In this formula, M is mass again, V is velocity, which is speed, and in the first half of the equation, this is just the speed that the cue ball is going to reach. Second half, these are the speeds after the collision. So let's try a word problem with this formula. If a 170 gram cue ball traveling at 5 meters per second hits the 6 ball, which was at rest, how fast will the 6 ball travel after the contact if it weighs the same and the cue ball leaves at 3 meters per second? Okay, so for this problem, we know that the masses are the same, so M1 equals M2, and both of those equal 170 grams, which equals 0.17 kilograms, which we'll use again. Also in this equation, we know that the cue ball traveled at 5 meters per second at first, so V1 equals 5 meters per second. We also know that after the collision, the cue ball travels at 3 meters per second, so it slowed down, so V1 final is equal to 3 meters per second. Now, what we need to find out is how fast the 6 ball moved after the collision, which is V2. So, to plug this in, all we have to do is put 0.17 kilograms traveling at 5 meters per second that's going to be equal to 0.17 kilograms times 3 meters per second, which is the cue ball, plus 0.17 kilograms times something, V2. Now, all we have to do to solve this is find V2. So, with quick multiplication, we can find that this side of the equation is 0.85, and this side is 0.51 plus 0.17 V2. So, subtract the 0.51, and we'll get 0.34, which equals 0.17 V2. All we have to do now is divide by the 0.17, and we should get our answer, which is 2 equals V2. So the 6 ball left at 2 meters per second after hit by the cue ball. Now, let's see how this problem would change if instead of first traveling at 5 meters per second, the cue ball was traveling at 6 meters per second, and after the collision it still traveled at 3. All we would have to do to change that would be to put 0.17 times the initial 6 meters per second, which is going to equal 0.17 times the final 3 meters per second, plus 0.17 times V2. Again, we can solve this formula, except this time it will be 1.02 rather than the 85. And this side is going to stay the same because we didn't change any of the variables. So, to solve now, we subtract the 51 again. And this time it's going to equal 0.51 on this side. Divide again. And this time we'll find out that 3 equals V2. An example collision. Let's look at our next formula. T equals R times F. In this formula, T is equal to torque, which is the amount of rotation. R is the radius, which is, in our case, the distance from center that you're going to hit the cue ball, and F is force. So in this equation, you can find out how much the ball will spin if you hit it at different heights from center at different forces. So let's look at a word problem. How much torque is produced if 25 newtons of force is applied at a distance of 0.015 meters below the center of the cue ball? Okay, so for this problem, we know that the distance from the center is 0.015 meters. We also know that the force is equal to 25 newtons. What we don't know is the torque. So all we have to do is solve. Torque is going to be equal to 0.015 times 25 newtons. Through a simple calculation, we could find that the torque is going to be 0.375 Newton meters, which is the unit of torque. Now, a higher torque means that it will rotate faster, so a lower torque than this would rotate less, a higher torque than this would rotate more. By increasing backwards torque on the cue ball, the spin produced makes the cue ball stop after the collision. In this graph, where force is a constant at 25 newtons, you can see that hitting the cue ball at different heights can produce greater or lesser torques. Torque and height are directly proportional. Let's look at our last formula. Angle of approach equals angle of departure. Okay, for this formula, what it says is that when the cue ball or another ball hits the side rail at a certain angle, it's going to bounce off at the exact same angle. Now, how we can use this is, let's look at a word problem. Let's say an object ball rests in line with the side pocket at a 30-degree angle to the side rail. What angle should we hit the rail to pocket this ball? Now, this is an easy problem because the angle of approach equals the angle of departure. So we need to hit it at an angle of 30 degrees to the rail to get it to hit this ball in. And this is true for any angle. If this angle was 50 degrees, we need to hit it at 50 degrees. If this angle is 10 degrees, we need to hit the ball at the rail at 10 degrees. So this is a very simple formula, but has very, very strong use in the game. Angle of approach equals the angle of departure. In this graph, you can see that the angle of departure is always equal to the angle of approach, and they are directly proportional. In this video, you've seen how hitting the cue ball with higher force results in a higher velocity. You've also seen how momentum is conserved in collisions. You've seen how torque can be produced and the effects that it can have on your game. You've also learned the angle of approach equals the angle of departure, and seen an example how this can be used in the game. Thanks for watching this video, and I hope you've learned something about the physics of pool.